When you have similar solids, their areas, that could mean lateral area, base area, or total surface area, and their volumes are related to each other too, but not by the same ratio as their heights or lengths or radii. For example, if we had these two squares, which are similar because their corresponding lengths have the same ratio. If it's a square, then both are the same lengths, but 2 meters is twice as big as 1 meter, and obviously this 2 meter is twice as big as that meter. So this square is twice as big. The ratio of similarity between these two is 2. But if you looked at their areas, this area 1 times 1 is 1 meter squared, and this area 2 times 2 is 4 meters squared. It's not twice as big. 1 and 4, this area is 4 times as big. It's because the area comes from multiplying this length, which is twice as big, times this length, which is twice as big, and it ends up being 4 times as big. That generalizes to any similar shapes in 2 or 3D. So the example that we saw last with these two whose ratio of similarity was 2.5, the areas of these two, and that could mean just the lateral areas, the base areas, or the total surface areas, is 2.5 squared. That's the ratio between them. The same ratio as one-dimensional, but squared, times itself. That's going to be true for any similar solids, that whatever the ratio is for one dimension, the area, any areas between the two shapes, will have a ratio of the same number squared. Here that turns out to be 6.25. You can use 2.5 squared or 6.25, they're equivalent. And the volumes, being three-dimensional, are going to have a ratio of 2.5 to the power 3. That's an easy way to remember that. So just to give you the information about what things are related in what way, any one-dimensional measurements, heights, length, radius, anything measured in just a regular unit of length, that is going to be related by the 1D ratio, just the regular ratio. And any 2D measurement, meaning any area, is going to be that measurement squared, and any 3D measurement, which only relates to volume, is going to be the same ratio to the power 3 cubed. So if you had the 1D ratio, you would get to the 2D ratio by squaring it. That's how they're related. And in a problem where you might have to work backwards, you would take the square root. So as an example, if we had the information that two shapes were related by a similarity ratio of 7, meaning that one shape was 7 times larger than the other, the 2D ratio, meaning the surface area, would be 7 squared, 49 times larger than the other. And working backwards, if we had two shapes whose areas were related by a ratio of 121, so one shape had an area 121 times larger than the other, means that the lengths of those two shapes would be 11 times larger one than the other. The square root, sorry, just to look back at that. It ends up being the square root of the 2D ratio. And the same idea applies to the 1D versus 3D ratio. If you had the 1D ratio, you would cube it to find the 3D, and working backwards, you would take the cube root. So for instance, if I gave you the 1D ratio, so if one shape was 6 times bigger than the other in its length, height, radius, or anything 1D, it means that the areas would be 36 times larger and the volumes would be 216 times larger. And if I had the 3D ratio, the only way to find the 2D ratio is to find the 1D ratio first. I can only get from 3D to 1D by taking the cube root, and then I'd have to get from the 1 to the 2 by squaring it. So the first step here would be to take the cube root, which turns out to be 5.4, and then the 2D ratio, the area ratio, ends up being 29.16. So in an example like this, where it says that the two areas of these shapes have a ratio of 16, means that this area is going to be 16 times larger than this area. That's true for any individual face or for the total surface area. That because it's an area, is my 2D ratio. To figure out the missing lengths, I need the 1D ratio, which means I have to take the square root. The square root of that ratio, 16, is 4, and it means that each 1D measurement is 4 times larger in the larger prism than in the smaller one. So now I can just set up ratios to find each one. For this one, I know it's related to this length 10, and I know that this is 4 times bigger. That works out to be 40. For this one here, y, which corresponds to the 3, and y is the larger one, I know that it's going to be 4 times larger than 3, which works out to be 12. And for this one here, z corresponds to 12. I know the ratio of similarity is 4, but z is the smaller one. So I'm going to divide by 4, and that works out to be 3, just like this measurement here. Turns out that that is a square. The same idea applies to two solids which are similar. You have to be told that they're similar or have an indication that they're similar. And if I'm told that the ratio of the volumes is 27, volume is 3D. If I wanted to figure out the ratio of areas, the only way to do that is to start by finding the 1D ratio, which I'd find by taking the cube root. That works out to be 3. So the ratio of areas is that 1D ratio squared. And in class, we'll talk about what letter we use for that. It means that the ratio of areas here is 9. And finally, it says that these two are similar, and it asks you to find the volume of the larger pyramid. The only thing I can start with is the 2 corresponding measurements that I have. Because I have 2 area measurements, I can figure out the ratio of the areas. The ratio of the areas is the larger area divided by the smaller one. Here that works out to be 1.96. That is my 2D ratio. It's what we call K squared. We haven't spoken about K, but it's the 2D ratio because they were both areas 2D. And using that, I can figure out the 1D ratio because it's the square root of that. I know that that works out to be root 1.96, which is 1.4. And now there are 2 options. What I can do is I can figure out the height of this pyramid using the 1D ratio and then calculate the volume. Or I can find the volume of this one because I already have the area, the base, and the height. Then I can find the 3D ratio and multiply that. Either one should work out the same, but just to show you, suppose we use the 1D ratio. I would find the missing height here. It works out to be 9.8. It makes sense. This one is larger by a factor of 1.4. It should be a bigger number. Then I would find the volume, area base times height divided by 3. Sorry, that works out to be about 128.05 centimeters cubed. And if I had done it the other way, I would have to find the 3D ratio, which I know is going to be 1.4 cubed. Then I would find the volume of the smaller pyramid, 20 times 7, area base times height, then divided by 3. And then I know that this volume has to be the 3D ratio times larger than the smaller volume. So we take the smaller volume, multiply it by the 3D ratio, and it means that the larger volume works out to be about 128.06. They're only off by a little bit because of rounding. And that's how you solve for missing values.